In Chapter 12, we will be looking at statistics. So if you're not familiar with statistics, statistics is the act of collecting, organizing, analyzing, interpreting, and drawing conclusions about numerical information. And that numerical information, and it's usually numerical information, is what we call data or data. Either way is correct. Again, this is usually going to be numerical information. For our purposes, all the data that we'll be collecting will be numbers. There are two types of statistics. The first is descriptive. That's what we're going to be doing. Descriptive is the act of the collecting and organizing, analyzing, and interpreting data. But we don't do inferential statistics in Math 100. Inferential statistics is when you actually draw a conclusion about the data that you collect. So what we're going to be doing is just basically collecting data, organizing it, and measuring it. That's going to be our main goal for this particular course. Well, first of all, where does our data come from? So for each research where you're going to collect data, you'll need a population that you're going to consider. Now, it's impossible to collect data from the whole population, typically. So what we do is we collect a sample of our population, and that's what we're going to base our information on. So when we talk about a population, that's a set of all people, or it could be objects that are being considered. A sample is just a subset of our population. Example 1, we have a city commissioner who wants to conduct a survey among the city's homeless to discover their opinion about required residence in city shelters from midnight until 6 a.m. So we're going to describe this population. So remember, the population is a set of all people or objects that are being considered. So this city commissioner wants to conduct a survey among the city's homeless. So the population is the city's homeless. And he's going to be looking at their opinion. So it's this particular city's homeless population. Now, the commissioner suggests obtaining a sample of the population because it would be impossible to talk to every homeless person in the city. So what this commissioner is going to do, and this is in part B, is to obtain a sample by surveying all the homeless people in the city's largest shelter on a Sunday night. So the question is, does this seem like a good idea? So you want to collect your sample of your population so that the sample actually represents the population. So when we think about just surveying homeless people that are already in a shelter and just on a Sunday night, that's actually not a good idea. It would not give you a good sample. Is think about what this commissioner is trying to find. He's trying to discover the opinion of the city's homeless. So if he only talks to those that are already in a shelter, chances are their opinion will be favorable to a required residence in a shelter from midnight till 6 a.m. So he's not really getting a representative sample of the homeless population, just those that would agree with the required residence in a city shelter. So the opinion would be biased. And for a number of reasons. One, the homeless that they would be talking to are already in a shelter. Two, they're only talking to homeless people on a Sunday night. So really what we want is what we call a random sample. A random sample is obtained in such a way that every element in the population has an equal chance of being selected. Now you can't select every person in your population, usually, because a population is just too large, or maybe it's just too hard to survey each person in your population. But they should have a chance to be selected. Now, just talking to homeless in a large city shelter on a Sunday night does not give every homeless person in this particular city a chance to be selected. So maybe a better idea would be to conduct surveys both in shelters, outside of shelters, in different neighborhoods, not just the city's largest shelter. So different neighborhoods of the city on different days and also on different times. So at least you give everybody in the population a chance to be selected. And that's really what we're concerned with. We're concerned with a random sample. Something about statistics, and you see statistics all the time. 3 out of 4 dentists prefer Trident sugarless gum, and so on. The point is, you have to make sure that the data is based on a random sample. Because if you start out with a junk sample, then you can conclude nothing. So in statistics, it's this little saying that says, start with crap, end with crap. Your sample has to be good. If your sample is not a good random sample, then anything you collect is actually useless. Let's say that we did collect some data and we have a good random sample, like the one we're going to look at in just a second. Well, oftentimes when you collect a bunch of data, it's just a string of numbers. It has no meaning. So to sort of see if there's any meaning or correlation with the data, we like to organize it. So we're going to look at ways to present or organize data. Suppose researchers are interested in the age that adolescent males have the greatest growth. So we have this random sample of 35 10-year-old boys. They're measured for height and then measured each year until they reach 18. So 10 years old to 18 years old. The age of maximum yearly growth for each subject is given in this list of numbers. So again, I'm looking at this list and it's kind of meaningless to me when it's presented in this way. So I want to organize it so I can maybe see if there's some correlation between age and maximum yearly growth. First of all, note that each one of these numbers is what we call a data item. So a data item is a single piece of data. So this number 12, this first number 12, this represents a single data item. This is a single adolescent male who had his greatest growth or maximum growth at the age of 12. The next number 14 is another boy who had his maximum growth at the age of 14, and so on. So notice that each one of these data items represents a different boy. However, when we look at the numbers themselves, that's what we call the data value. So yes, the first number 12 represents one boy, but we also have another number 12. So the data value is actually the value of the number. So the data value for these is 12, although they represent different boys. Okay? So data value is just looking at the number itself. Now, one way that we can arrange all of this is in what we call a frequency distribution. Frequency distribution, it's just a table. It'll organize our data into 2 columns. The first column is going to be the different data values we have, and typically we go from the lowest to the highest, but depending on your research, it doesn't have to be that way. So that would be this first column. The data values in our case would be the age of maximum growth. The second column will be what we call the data frequency. How many are there? So that would be the number of boys. For example, when you look at that string of numbers, the smallest number is 10. That would be the data value. So how many boys had their maximum yearly growth at the age of 10? It's easiest for me when I go through the list to kind of cross it off as I go along. So there's one. It looks like just one. So that frequency is how many of those data values you have. The next one, remember we're going from lowest to highest, would be 11. So how many boys had their maximum growth at the age of 11? If I go through this list, I see 1, 2. And then at 12, we have 1, 2, 3, 4, 5. So at the age of 12, there's 5, and so on. So I'll go ahead and complete the table. 13, we have 7. For the age of 14, we have 9. Age of 15, I counted 6. Age of 16, I counted 3. At the age of 17, 1. And then 18 is 1. So this table is complete. Now, if I add up the column of the frequency, remember this research was based on 35 boys. So that should add up to 35, which it does. So here, oftentimes you'll see this N. N is the number of data items or the total of that frequency. So that would represent the 35 boys in this particular study. For just a second. When we look at this previous example, now that it's organized, I can see that at the age of 14, for this particular sample, that's when most of these boys had their maximum growth. So maybe we can think, oh, maybe 14 is the magic number. Well, this was a very small sample size. There was only 35 boys. So maybe this will lead us to say, well, maybe if we increase our sample size, will 14 still be that magic number? And that's what you usually do in statistics. You start out with something small, see if there's any trend going on, and then you just, if possible, increase your sample size and see if you can get some sort of conclusion on your data. There's another way that we can go ahead and organize our data, and that would be by what we call a grouped frequency distribution. So this is just another table, but instead of listing every single data value in the first column, maybe that's not so useful. Okay? In our previous example, it was useful. And in fact, let's go back to this group frequency distribution. So in this particular case, example 3, we're going to use classes instead of individual data values. And I commonly use classes when I try to figure out the grades for students, right? So when you're talking about a B grade, that's going to be between 80 and 89. So maybe I don't want to list every student's score. Maybe I just want to group them in their classes. And that's what this example is about. So again, we have 2 columns. The first column is going to be our groups instead of data values, but the data frequency is still going to be the second column. Example 3, we're told to use these following classes, 40 through 49, 50 through 59, 60 through 69, and so on. And we're going to construct a group frequency distribution. So there's 37 student exam scores listed. What we're going to do is count up how many of these student exam scores were in the first class, which is the 40 to 49 class. So again, when I look at my list, do I have it? Oh, I have a 41 right here. So I have one student that scored in the 40 to 49 range, so the frequency is 1. The 50 to 59, I have 1, 2, 3, 4, 5. It looks like 5. And then we'll keep doing this. 60 to 69 would be 4. 70 to 79 is 15. 80 to 89 is 5. And then 90 to 99 is 7. Now there's supposed to be 37 student exam scores. So when I add up the frequency column, it should be 37, which it is. Oftentimes when you do these exercises on my lab, it won't have that total at the bottom. It'll just have the 2 columns, but sometimes it'll have the total on there. So let's look back at this grouped frequency distribution. When you look at, and here we're going to ignore the first and the last classes because those can be a little bit off. So for example, if these were really representative of exam scores, maybe instead of going to 99, maybe I would go to 100. It's possible to get 100% on the exam. Maybe I wouldn't start at 40, maybe I would start at 0. So typically we would ignore the first and the last class and then have all the other classes a uniform width apart. When I look at the difference between these classes, the width is going to be 10. That's the difference between them, and you can either look at it as subtracting the 40 or the 50 and the 60, 60 and 70, 70, 80, looking at the difference between those, or looking at the 59 to 69, 79 to 89, and so on. So in each class, there's 2 numbers. The lower class limit is going to be the left number in a class. So if I were to list all the lower class limits, it would be the 50, 60, 70, 80. And let's assume that I did not change and cross this first out. It still counts, the 40, and then 90 still counts. So if I were to list the lower classes, the lower class limit for each one of these classes, it would actually be, there I go again, it would be 40, it would be all of them, 50, 60, 70, 80, and 90. If I was going to look at the upper class limit, that's the right number in each one of the classes. Now here I'm going to assume that I didn't put a line through the first one. That would be the 49, 59, 69, 79, 89, and I'm going to go with the original 99. And so on, 49, 59, 69. Okay. So the class width is going to be the difference between the lower limits. And then it says you may exclude the first and the last class. So like I said, the first and the last may be skewed a little bit off, but the remaining classes should always be the same distance apart. So what you're doing is you're subtracting the lower limit. So the 50 and the 60, when you do the subtraction, it's 10. The difference between the 60 and the 70 is 10. The difference between the 70 and 80 is 10. In our case, our class width is going to be 10. All right, so we organized our data into tables. And on that last example, you notice that most of the students scored in the 70 range, which is about a C average. Now we're going to look at another way that we can organize data by either a histogram or a frequency polygon. Basically, those are just graphs. We'll go back to the frequency distribution for the boys' maximum yearly growth, that table that we had before. And that's fine. When I see this data, I can see, oh, at age 14, I had 9 boys that had their maximum yearly growth, and that's the highest frequency. So maybe increase the sample size, do some more research, see if 14 is the average age for maximum yearly growth. But another way that I can organize this data is by looking at a bar graph. Statistics, they call this a histogram, is just a bar graph. So if you notice in this bar graph, I put the ages, remember those were our data values, at the bottom. And then for each one of those ages, the bar represents the frequency. Just another way to organize data. So visually it's appealing. We could see that we still have this maximum growth. At the age of 14 years old, there were 9 boys. Another way that we can organize the data is in a frequency polygon. So the frequency polygon, it's just a line graph, but in statistics they call it a frequency polygon. So just another way to organize. Again, bottom, we have our data values, which would be our ages, and then the frequency would be the height of this graph. Again, I could see that there were 9 boys that had their maximum growth at the age of 14. So we can also combine the two. Have a bar graph and a line graph together, or histogram frequency polygon together. So these are just picture ways to organize data, and you've seen other graphs as well, such as pie charts. The last thing we're going to look at is another way to organize. That would be the use of a stem and leaf plot. So when we look at our stem and leaf plot, it's a way to organize numerical data in a table format that also has sort of a picture quality to it. Our stems are going to be the tens digits, and our stem and leaf plot we typically use for 2-digit data values. The leaf will be the unit digit or the ones digit. We're going to construct a stem and leaf plot for these 28 student exam scores. So if I look at these numbers, these different data values, I could see that the lowest score is in the 40s and the highest score is in the 90s. And I have 40s, 50s, 60s, 70s, 80s, 90s. I have them all. So my stems are going to be the 10 spot. And when I talk about the 10 spots, it's that, like in 73, that would be the 7. In 58, that would be the 5, and so on. So what I'm going to do is I'm going to organize the stems from smallest to largest. So my lowest score is 41, so I have a stem of 4. And then I have scores in the 50s, 60s, 70s, 80s, and 90s. And now for the leaves, that would be the 1 spot. In my lab, they might organize the leaves as well from smallest to largest, but that is not necessary, and that's not what I'm going to do. What I'm going to do is just look at my table and start with the first number. The first data item is 73, so it has a stem of 7 and a leaf of 3. So where the 7 is, I'm going to put a 3. So that represents 73. The next one is 58, so 5 and 8 for the leaf. 68 would be 6 and 8. Notice that I'm not even putting my leaves from smallest to largest. 75 has a stem of 7 and then a leaf of 5. So you want to try to line up the leaves also in columns. Sometimes it's helpful if you draw lines just so things can be neat, but that's not necessary. Let's keep going on 90. I have 41. The 50s would be 8, 2, 0, and 7. The 6s would be an 8, and there's a 69. The 70s would be 73, 75, 79, 77 would be the next one. 75, 75, 73, 73, 76, 77, 71. And then the 80s would be the 87, 83, 89, 89, 81. 90s, I have 94, 96, 99, 97, and 95. And that's our stem and leaf plot. If we look at this stem and leaf plot, we could see that the stems give us all the different scores. So we could see we have scores in the 40s, 50s, 60s, 70s, 80s, 90s, and so on. But we also see which score we have the highest range in, and that would be all the scores in the 70s. So it's this kind of neat way to organize the data so that it also kind of looks like a sideways bar graph. So you could see where most of your data items fall. And that's it for 12.1. Again, that's just collecting data and organizing it in tables and graphs.